Hello everybody, welcome to the video for the lesson number 6 on working with exponential models. So in this lesson we're going through and just working with a couple different tricks and things that we can use with exponents to kind of start to help us get into some of the thought process that we'll need in the future lessons of this unit. So one of the things that we learned in class today was that you can go through and rewrite an exponential model by using your exponential rules. So number 1 says to write an equivalent function to v of t equals 32,000 times 0.81, all to the t over 12. Well, one of the things that we know is that t over 12 is really 1/12 times t. So it means I can rewrite this as v of t equals 32,000 times 0.81 to the 1/12 power, all to the t power. Now it says to round the values to the nearest hundredth, so that means I want to evaluate this. So if I go to my calculator, I could type all that in. So 0.81 to the 1/12 power. Notice in my calculator, I have the new calculator, so I don't need to do this because it'll automatically go up in the exponent. For those of you with the older one, parentheses is probably going to be helpful here. So I'll round that to 0.98. If you're not getting 0.98, you're probably typing it in wrong. So that means I could take this and rewrite it so that I get 0.98 here. Now, looking at this, because of what this number is, I know this is actually going to be exponential decay without even graphing it. Number 2 says, Jack says that P of t is going to represent exponential decay because the number in the exponent is less than 1. Comment on Jack's claim and reasoning. Well, the number in the exponent is really only going to be useful to us if we compare it to the number in the base. Now, since the base is more than 1, what I essentially have to do is evaluate 2.7 to the exponent of 0.039. Because if I do that, it tells me what my base is. So if I do 2.7 to the exponent of 0.039, that gives me an answer of 1.03. So Jack's claim is wrong because the base is actually more than 1, not less than 1 like he thought. So using exponent rules, we can kind of disprove Jack's claim. The last question I'd ask you to do here is very similar to the last question in the notes, where we have two different functions. I'm asking you to evaluate both of them and state a value where they're intersecting each other or they're the same as each other. So the one thing that's interesting here is, if you notice, unlike with the question that we did in class, the scale is not done for us. So the first thing I want to do before I even start figuring out the scale is graph these two things. So I want to see an estimated point of where they intersect each other so that I could clearly come up with our x and y values, or in this case t and y values. So let's go to our calculators. So I want to plug in the first equation there, and just keep in mind you got to kind of look at some of the things that we know about. So like, you know that the number in the base is less than 1. If you raise it to the exponent, it's going to be a decay graph. Same thing with the b of t function. I have a number more than 1 but to a negative exponent, making that less than 1. So it's again going to be a decay graph. So both of these should be decay graphs. I also see that the first equation has a y-intercept of 800. So that's going to help me when I'm trying to figure out what my window range is going to be. And then if I graph the other one, the second one's going to have a y-intercept of 400. And that basically tells me what the y values are going to be. So I'm going to start my y values at 0 and go up to 1,000. I'm just going to go to 1,000 because it's more than 800. And the y max, I don't know what it's going to go to. I'm going to start by guessing 20. So here I see two curves that come down, right? 20 actually might even be too much. Let me change that to, we'll say like 15. That's okay. Right, you want your intersection to be somewhere in the middle. So what we see is originally a of t, which on my graph is the blue function, is going to be a larger value than b of t, which is the red function. But at some point right around here, they intersect each other. And at this point, from here on out, the equation of b of t is larger than the equation of a of t. So this is the point at which they're equal, and this is also the point where b of t's equation surpasses a of t's equation. So if this was a real life situation and we're talking about, say, like money or something like that, we could say that this is the point where the one equation surpasses the other one or starts to become more valuable. Similar to the question we did in class about the car's depreciated value versus what the insurance company thinks it's worth, so that you can kind of start to see when the car is equal in value to what the car company's insurance company is going to be able to pay you. So when graphing this, I want to go out to, we'll say like 15, because it looks like 1, 2, 3, 4, 5, 6, somewhere around 6 or 7 is where the intersection point's going to be. So when making my scale, I want to at least go out here to like 10 or 12 or something like that. So it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 20 boxes here. So if I make each set of 2 boxes worth 1, that'll get me out to 10. 10 should be good enough because I can estimate from my graph that the intersection point is going to happen around 6 or 7. And then for the y values, I also have 20 boxes, and I need to go up to 800. So if I divide 800 by 20, I can make each box worth 40. So I could go 40, 80, 120, go up in sets of 3 or something like that. So 20, 40, another 120, so that'd be at 240. 20, 40, 60. I'm sorry, what did I just say? 40, 80, 120. 40, 80, 120, so 360. And just keep going up by that 120 marker, right? So we'd be at 480, which will tell us that this is 400. That's important because that's where one of them starts. This is not the only scale that works, by the way. Just the one that I thought of here that will kind of help us. All right, so we go up 120, 120, 120, 120. 720. I'm short a box. I must have missed one somewhere. Let's make 800 up here. So because each of these is worth 40, I can label some of my points here. So let's start by graphing one. So if I go to my table, let's graph this first one. So 800, and actually let me just quickly take a picture here. This will make my life a lot easier. So when graphing this, we want to start and again, like we did in class, it's an estimate. It's never going to be perfect, right? Try and get some good points whenever you can. So let's see here. So let's graph the first one. So at 0, I'm at 800. So that would be at the top of my graph. At 1, I'm at 565. So 1, I got 480. Each one of these boxes worth 40, so that would be 520, 560. So I'm right about there. 2, I'm at 400. 2, I'm at 400. Right about there. 3, I'm at 282. So 240 plus another 40 is right about there. At 4, I'm at 200. Should be right about there. 5, I'm at 140. Right about there. 6, I'm at 100-ish. So in between 120 and 80. Actually, I made too short. All right. 7, it's at 70, so each one of these is 20, 40, towards the top of the 80 box. And we could start to see what this looks like. So we have our graph that's coming down, touching each of these points. Try and draw a smooth curve if you can, and then you have your idea here. The next one. So if we go to graph the next one, so I'll do this in a different color. We'll go red, right? Start at 400, so here. Then we go after 1 is 315. 2 is 250. 3 is 200. Notice it's still below this graph, right? It didn't happen to like close to 6. 4 is 160. So I have 120 plus 40 is 160. Still below. Right, if my purple curve was even better, it'd still be way below. 5 is at 140. So 120 plus 40, so 140 is about even. Right? 6 is where they're almost the same. Look at that. Right at 6, they're almost even in my table of values. So what that tells me is I'm definitely going to be close to 6, 5 point something. So 6 are almost the same. And then 7, we're a little bit above, a little bit above, a little bit above for the rest of the graph. So this function comes down, kind of stays below, and eventually intersects and surpasses the first graph. So what I'm interested in is where is this point of intersection, which I can totally find right in my calculator, because that's what they're asking you to do. State the value for t where they're intersecting each other to the nearest whole number. So if I go back into my calculator and go to the graph, second, calculate, go to intersect. Since it's only one intersection point, I can just enter 3 times, and it'll totally work. So the intersection point is at 6, 100. So they want to know, state the value where they're equal. So you could say t equals 6, which is what we initially estimated by looking at the graph. Essentially what we're able to estimate from our graph if we sketched it good. So not really a terrible question, right? Again, something we could totally put on a quiz or a test. Hopefully this video helped. I apologize for my bad handwriting on the computer here. Um, I had to use the other computer because of the silly calculator stuff, but hopefully that whole part helped you. All right. Regents class, expect a quick quiz coming up soon. Accelerated class, full period quiz at some point next week.